are dealing with the threat of fire, and what are the traditional practices they are using to design the structural elements which are fire resistant, which can perform safely in case of a fire. And once you have that idea that what are the traditional practices which people are using, then I would be giving you a brief idea about how does a typical structural element such as a beam behave when it is exposed to fire. What are the different kinds of stresses and what kind of axial forces, bending moments can get generated when a structural element such as beam is exposed to fire. And when I would be telling you about the behavior of this beam, I would highlight the differences between a unrestrained beam and a restrained beam, and I would let you know more about what are the differences between these two kind of beams in the later part of the presentation. And then we would understand that how people in the past have had a basic understanding about the behavior of these structural elements. How did they generate their understanding? How did they make a common law that these structural members will behave in a particular way? And to understand the behavior of these structural members, they conducted large-scale testing where they made the whole building with 8-9 floors and then exposed different parts of the building to the fire to understand that how different structural elements such as beam, column, slabs are behaving when they are exposed to fire. And they did this. They followed this expensive technique because conducting a fire experiment on a real structure is very expensive. So even then they used this expensive technique, expensive process, because they did not have any prior idea that how the structure behave in case of such a extreme scenario, because they would never have imagined that what would be the effects of the fire on a structure. So in order to understand that, large-scale testing was being conducted in the past, and they made a basic understanding, and certain laws and fire-resistant designs were developed using the knowledge of these large-scale testing. And in the final part of the seminar, I would be telling you about how did people have develop finite element models for these structural elements, and the need to develop these finite element models was because you can not always conduct these large scale tests to understand the behavior, because conducting these tests is very expensive and you need large experimental facilities, and all the research institute in the world do not have these kind of facilities. So in order to avoid that huge expense in conducting these tests, researchers have developed finite element model in the past for these structural elements, and in these finite element modeling, they exposed these beams, columns, and the whole structure to the fire, and then they compared the results from these finite element model with the real tests which they have conducted in the past, and this is how they establish accuracy in their finite element model. So if they are having a fairly accurate finite element model, then they could use this model for a different fire scenario which they have not exposed their structure in the past. So this would be the outline for today's webinar. So here I would start just by giving you a definition of fire in the context of structural engineering. That for a structure, fire is nothing but a kind of load. And similar to the other kinds of load, such as the static load, the load of the furniture, the load of the human beings, the occupants in the building, that is also a kind of load. So in the similar sense, that fire is also a kind of load. And why does fire is a kind of load for a structure? You would understand here that what does a load do to a structure? A load induces different kind of stresses in the structure. Suppose if this is a building with different stories, with 4 stories, and at every story there is a load which is acting in the downward direction, and this load may be coming because of the occupants which are living in this building, and it may be coming of the furniture and the furnishing which are present inside the building, and that is acting in the downward direction. And what this load is trying to do, suppose if we take out this beam outside and magnify it to see it, what in actual reality what is happening with that beam. If this is being loaded from the top, and what this load is trying to do, this load is trying to bend this beam in this way. That this load is trying to bend the beam in the downward direction, and due to the bending, the top of the beam is experiencing a compressive force, whereas the bottom has been extended. If we draw a line from the top, we can see that the top fiber has been contracted, and the contraction is because of the compressive stress, and the bottom fiber is experiencing an extension, and this extension is because of the tensile stresses. So there is the stresses which are being induced because of that load on the structure, and the nature of those stresses is the compression at the top and the tension at the bottom. So if we draw the pattern of the stress for this beam, it would be like compression at the top from the center line and tension at the bottom. So this would be a kind of stress pattern for this beam. And I said initially that the fire is also a kind of load. It means that fire is also inducing some kind of stresses in the structure. And what kind of stresses fire can induce in a structure? You would understand by this similar example, where this is a beam and we are stopping it to expand in the axial direction. This is its axial direction, and we are stopping it by providing a support at the end. This support is not allowing it to expand, and now we have applied it fire which increases the temperature of this beam with an amount of delta T. So when we are increasing the temperature of this beam, this increase in temperature is trying to expand this beam. This beam will try to expand beyond these supports, but as we have stopped this beam from expanding, so it means we are putting a compressive force to stop it. This beam would be in its initial position only if we are applying a compressive force, and we are stopping it from expansion just by applying a compressive force. It means the effect of fire is to induce this compressive force in the member. So a normal load was inducing compression and tension in this way, but if fire is inducing compression both at the top of the section, at the below of the section, at the bottom of the section, both, we are experiencing a compressive force. So this compressive stress is a kind of additional stress which was not acting when there is no fire. So because of this additional stress, the structure could fail. So what fire is doing to a structure, it is putting extra stresses on the structure, and to take care of those extra stresses, we need to design the structures against fire. So fire does two things to a structure. One is it induces extra stresses when the temperature is increased inside the structure, these extra stresses. And the second thing which fire does to a structure is to reduce its capacity. The material properties get reduced, the material degrades. If initially the material can take a stress of 200 per millimeter square, and you heat up this material, suppose up to 500 degrees Celsius, then it would only take around 100 Newton per millimeter square. It means you have reduced its capacity. The fire reduces the capacity to take the stress. So it adds the stress to the member, and at the same time it reduces the capacity. So it is acting in the two way. A structure could only fail. Suppose this is a beam. This is a beam, and you are applying a load. How can you fail this structure? You can fail this structure in two ways. Either you keep on increasing the load. You keep on increasing the load until it is more than its capacity. It means you have increased the load so high that its capacity is not capable of taking that load. Then the structure would fail. This is the first scenario when the structure could fail. And the other scenario is that if you don't increase the load, you keep the load constant. The other scenario by which you could fail this beam is by reducing its capacity. So if and what does a fire do? It reduces the capacity of this material. So the fire is doing both the things. It is increasing the stress. It is at the same time it is also reducing the capacity. So both the only two way by which a structure could fail, fire is doing both. That is why fire is so important for structural engineers to study, because it acts in a negative way for a structure and it leads to the failure of the structures in many cases. But as you have understood the importance of studying fire in the context of church, that what structural engineer in the industry or people in the research field, what they are using to design the structure against fire. So this slide is about that process, what people in the industry and academia are doing to design the structure. What they are doing, they are following a standard approach which was developed around 80 to 100 years ago. And according to that approach, what they were assuming that if the temperature of the structural member is within a range of 550 degrees Celsius, if you are applying heat to a structural member, and the temperature would increase. But the temperature should not increase more than 550 degrees Celsius. It should not go beyond 550. And if it is in the range of 550, it is below 550, then they consider that the structure is safe. So this is a kind of approach which they are using, and it is not representing any kind of magnitude of stress are coming because of fire. It is not showing anything that by what amount the capacity of the structure is reduced. So it is not representing anything in practice. And the other disadvantage of this approach, which people are still using, is that when they apply fire to the structural members, they consider that the temperature would vary according to this standard time temperature curve, as you can see here in this slide. The time is increasing, the temperature is also increasing, and we call it a standard time temperature curve, which was developed by both researchers in USA and UK around 100 years ago, and they both give the same kind of output, as you can see here. They both are giving similar nature of time temperature curve. And the disadvantage with this kind of fire scenario which we apply to design our structure is that it keeps on increasing. If you increase the time, it will keep on increasing. But in a real life scenario, what does happen to a fire? If you ignite a fire, and once the all available fuel is burned within the compartment or in the building, then after you don't have any more fuel to burn. Then once the fuel is finished, the fire will automatically start to cool down, and the temperature would come down. But this is not happening here in this case. So it is not representing a real fire scenario. But as they are using it, so that is the drawback of using this methodology, that it does not represent a real life fire scenario. This is a typical setup which people use to conduct standard fire tests. This is a setup to test a column. A column is the vertical member in a structure. As I have shown you, that if this is a building, this is a beam where the vertical load is acting. This vertical member is a column. So this is that is why they have placed in a vertical direction. And this vertical member, they applying a load from the top. The load is being applied from the top, and the fire load is applied through the flames from the burner from all sides of this column. It is being exposed to fire. And this is how they are testing. They are increasing the temperature by applying the fire, and they have applied a load on the column. So another drawback, the major one, which is associated with this kind of testing, is that they have isolated this column from the whole structure. In reality, this column is a part of the structure. It is attached to other beams and the other columns if there are more stories. The other columns, other beams are attached to this column. And if you are isolating it and looking at it in isolation and not assuming the connection with the other parts of the structure, then it is not a representation of the actual behavior. It would behave in a completely different way if it would have been connected to the real structure. So the kind of connection which it is forming with the other parts of the structure, that is missing. So it is also not representing the real connection with the rest of the structure. One, it is not representing the real fire scenario, and the second thing, it is not representing the real structure in itself. It is a part of the structure. So now you know the disadvantages associated with this kind of method, but still, as people are doing this, so the test criteria for this kind of testing is that your column or the beam, whatever you are testing using this method, should be stable. It should maintain stability. It means it should be able to carry that load which is being applied on it initially, and it should not lose its stability. It means it should not deflect too much. If it is your horizontal beam, it should not be deflecting like huge amount. So it means that it is stable if it is not deflecting too much. So it should maintain its stability, and if it lost its stability, it means you consider that it has failed. The other criteria by which you consider the failure of the structural member is the integrity. It means that if you are testing a beam, and because of the exposure to fire, it develops some cracks. And within those cracks, if you see any flame, it means that the structure is failed in the integrity. So this is another criteria by which you can assume your structure to be failed. And the final criteria is the insulation. Suppose you are hitting your beam from the bottom, the fire is being applied at the bottom, and the top surface is unexposed. You are not applying any heat to the top surface. So the temperature at the top surface should not exceed beyond 140 degrees Celsius. And if it exceeds more than 140 degrees Celsius, then you assume that your structural member has failed in the insulation. The insulation which you provided around it, it has failed. And if one of the criteria has met, it means you need to stop the test and you consider that your member has failed. So this is a typical setup of a standard fire test for a beam, and this beam is unrestrained beam. Unrestrained means when it is trying to expand, when we apply fire, this is a fire we are applying to this beam, and when this, because of the increase in temperature, this beam will try to expand. So when it is trying to expand, we are not stopping it from expansion. At the ends you can see here, we are allowing it to expand. The amount, whatever amount it wants to expand, we will allow it to expand. We are not providing any compressive reaction to stop it from expansion. So this is how they do a standard fire test for a simply supported beam. Here you can see that the free movement at the support, you are allowing it the free movement. So now you are, as you have seen in the very first slide, if you are stopping it from expansion, a compressive stress will come into the section. Now here in this case, you are not stopping it. So it means that with the increase in the temperature, you are not inducing any additional stress into your member. So what is the other thing which fire could do? If it is not inducing any additional stress, it could reduce the material properties. Then only it could affect your structure. So the stresses inside your member would be governed by the degradation of the material properties. That would be the important criteria in this kind of test where you are not stopping it from expansion. So where the free expansion is allowed, the behavior would be governed with the degradation in the material properties. As this is a steel beam and this is its temperature deflection curve, this as you can see here. So I think if you are not aware that the properties of the steel start degrading after the temperature of 400 degrees Celsius. Up to 400, the yield strength, the capacity to take the load of steel remains the same. It is not affected. And once the temperature of 400 is met and you increase the temperature beyond 400, then the properties of the steel, the yield strength in particular, start to decrease at a very fast pace. And that is why you can see here up to 400 degrees Celsius, you can see that the deflection in the beam is very low. And as soon as you keep on increasing the temperature beyond 400 degrees Celsius, there is a sharp increase in the deflection of the beam. And this sharp increase, the sudden increase in the deflection, we call it a runaway deflection. And at this sharp increase and the high increase in the deflection, we consider the beam or the member has failed. Failed in the load carrying capacity in the criteria 1. So now you know the behavior of a unrestrained beam, but in a real life structure, a beam is 99% unrestrained. It means you are stopping it from expansion. For example, if this is a column, this is a beam, and if you heat this beam from the bottom, it will try to expand, but these columns, as you can see here, will stop it from expansion. So these columns would bend something like this and will allow some expansion of this beam. So they are still applying some compressive force, which is stopping this beam from expanding. So this is what happens in a restrained beam. As you can see here, this is a restrained beam. We have applied fire from the bottom. As soon as the fire is applied, it will try to expand. And because of that restraint which we are applying through this support is not allowing it to expand. The compressive force is inducing. This compressive force you can see at the support. This compressive force will not allow it to expand at a very fast pace. But initially this would stop it from expansion, and at the later stage when the temperature would be very high and the strength of the material will be reduced significantly, then at that point your beam would deflect too much and the properties would be so less that it will not take load in a flexure action or in the bending action. Bending action means it has both compression and tension. The material properties has reduced so much, now it will act just as hanging as a cable. At this stage you could consider that the beam is just hanging and the load is just lying over it. So if when I say hanging as a cable, if you imagine that a cable, if you apply, this is a cable, if you apply compressive force to it, could it carry a compressive force? A cable cannot carry compressive force. If you apply compressive force, it will all gathered at one place, the cable. But if a cable is there, it is hanging, and if you apply a tensile force to it, it will get straightened up. Okay, under a tensile force. It means it can carry a tensile force. So at this stage, this beam will take care of this vertical load under the tensile action, because it is no longer able to carry the load under the bending action. Now it will take care of the load under the tensile action. And at the final stage, up till now, what was happening to the axial force? Initially it was increasing. The top is compression, the bottom is tension. The compression was increasing, and after a limit, when some local failure happens inside the beam, the compression start to reduce. Compression start to reduce and changes to tension. And finally, when the material properties has reduced so much that it does not even take care of that load under the tension also start to reduce. And at this point, we consider that the beam has failed. First, the compression would increase, then the compression would decrease and changes to tension. And finally, this tension would also not be enough to carry that load. And at that point, we consider that the beam has failed. And this is how the behavior of a restrained beam governs. And this graph is for restrained beam. At this point, the compression has reduced and the deflection started increasing. But at this point here, the beam again start to carry load under the tensile action. That is why you could see less deflection. And again, the deflection start to increase at a very fast pace when this tension also start to reduce. Means the beam is no longer able to take that load even under tension. Then we consider that the beam has failed. And this is how there are three stages of in the behavior of a restrained beam, and they compared to the only this kind of behavior in an unrestrained beam where there is no tensile action in the beam. So as you know that there is a very standard approach which is available, the standard fire test. And so why do we need to change this testing approach to design our structures against the threat of fire? Because you already know that there are so many disadvantages which are associated with this, such as the nature of the fire exposure, the time temperature curve, which gives you always increasing temperature, and the interaction of the column or the beam with the rest of the building. You are missing it. The interaction of that tested component with the rest of the building. So because it has so many limitations, and the main thing is that the economy. Because you are applying such a high temperature, because it is keeping on increasing, you are applying such a high temperature that the amount of money which developed countries such as USA and Australia are spending on the fire design is about 1% of their GDP. So to reduce this amount of money on the fire design, we need to come with a better approach, with a more performance-based approach. So that is why we need to study, or we need to find another method of designing the structures against the threat of fire. So in order to develop those methods which are different than the standard fire approach and are more performance based, various experiments have been conducted in the past. And one of the milestone experiments which were conducted by the University of Edinburgh team and the British team in 1995 on a Cardington steel frame. In Cardington, they have made a steel frame with actual dimension as that of a frame in real building. It was a full-scale model which they have tested by applying a fire, and they have conducting various tests. So here we would be discussing about two tests conducted by them. And in all the tests conducted by them, they have assumed that the beams are unprotected. It means that they did not provide any fire protection to the beam. And the other thing which they considered is that that the columns were protected. And the protection for the column was assumed because in a real structure also, you must have seen that there is no column which is visible to you. All the columns are either inside the wall or are surrounded by the concrete. So that kind of concrete surrounding the column act as a insulation for the column, and that is the reason for them to consider protected columns. And in all those tests, they did not experience any kind of structural collapse. So this was a Cardington frame where they tested different structural elements, beam, columns, or the frame, or the whole compartment. They have conducted so many tests in that facility. So these are the main 4 tests which were conducted by them. The test 1, you can see here. Here, they did apply fire only to this beam. This beam was exposed to fire, and they named this test as a restrained beam test. And why do they consider it as a restrained beam test? Because they were stopping the expansion of this beam through these 2 columns, C1 and C2. Through these columns were not allowing this beam to expand when the fire was applied. And this is one of the most remarkable tests to calibrate your finite element model. When you're conducting a finite element study on a software, then you need to first calibrate your model so it would give you results similar to the reality. And to calibrate that model, you need to verify your result with some experiments, and this is considered as the best experiment to calibrate your finite element model for the restrained beam. And the other test which they conducted was on a plane frame. It was test 2. This was conducted on the 4th floor. All of the tests were conducted on different floors of that facility. And in the plane frame, what they did, they applied fire all these beams, as you can see here, B1, B2, B3. Simultaneously, they all beam were exposed to fire, and all these columns, C1, C2, C3, C4, they were also exposed to fire. And this is a plan of the building, and if you see the elevation of this test 2, it would look like something like this. This is C1, C2, 3, C4, B1, B2, B3. So this is how they apply the fire to all these columns and all these beams. Everything was exposed to fire. And in the 3rd and the 4th test, they increased the complexity of testing by exposing the whole 3D area. The whole area was exposed to fire. Where there was slab also, there was a number of columns in the interior, columns at the edge, beams at the edge, the interior beams, because every structural element would behave in a different way. And to increase the complexity to that level that it can incorporate all kind of structural members, so that is why they increase the complexity here, so that it can include all kind of possible structural behavior in the fire. So during the first restrained beam test, they have made some important observations. And one of the most important observation made by them was that they observed cracks in the slab at the top of the beam. This is the restrained beam, and this is the top slab, the roof level of this beam, and they have heated this beam from the beneath, and they have seen that the cracks are happening here. And these cracks are happening because of the tensile force which is being induced here. I'll explain you the mechanics behind this. If this is a beam and the load is being applied at the top and fire is being applied at the bottom, it will try to deflect in this shape. So what would happen near the support at the midspan? The bottom would be in tension, the top would be in compression. But what happens at the support? Compression is at the bottom, the tension is at the top, because this fiber is being stretched like this. The tension will come at the top, and that is why at the top, because of the tension, we are seeing the crack, because concrete is a weak material under tension. So whenever you are exposing your concrete or you are applying a tensile force on your concrete member, it will crack.
And that is why they have observed a crack in the restraint beam test near the support, because the near support region is the high tensile force region, and they did not experience any crack at the center, because at the center the tension is at the bottom, and in your beam the I section, this I section, the steel section is at the bottom and the concrete slab is at the top. Since at the section mid-span the compression is at the top and the compression is taken care by the slab, and slab is strong in compression, that is why they did not observe any cracks in at the mid-span of the. But as the steel is equally strong in tension and compression, so it has taken care of this tensile force, and there was no cracking at the mid-span, and the cracking was only at the support of this section. So this was one of the major observation made by them. And another observation which was very important and proved to be very useful in further studies was the local buckling of this restraint beam. And when I say local buckling, it means that there is a local, means the bending of the beam is at very specific location, not the whole beam was bent significantly. Suppose this was the beam. The whole beam did not bend very significantly, only there was a bending at some particular location, and that is why we call it local buckling. And if it was a whole beam bending, then we would have called it global buckling. So the local buckling phenomena was observed. And because of that, local buckling happens in an early stage of fire, because under high compression, compressive force are coming on this beam in the initial stage, and that compressive stress is responsible for the buckling of this beam. And this as soon as this local buckling happens, the compressive force which was increasing because of the rise in temperature, this compressive force start to reduce because of that local buckling, and then changes to tension, and then you know that how does it decreases, even the tension does get decreased. So these were the major observations made by them during the restraint beam test, and some of the major observations made by them were during the plane frame test. And they observed that this kind of crushing happened in the column. And when they analyzed that what was the reason of this crushing to happen in the column, they found out that they did not provide the protection, the fire protection to the column, to the whole length of the column. They did apply up to this length, and above this length there was no protection, and it was directly exposed to the fire. As it was directly exposed to the fire, it experiences high temperature, and that is why they see this local crushing of the column. And after this test, they got a understanding that they need to apply fire protection to the whole length of the column to avoid this kind of sudden behavior or sudden crushing in the column. So this was the main learning from this plane frame test, that after the further test which they conducted after this test, they did apply the fire protection to the whole length of the column. And the phenomena of local buckling also happened even in this plane frame test. All the beams have experienced the local buckling. And another important thing which they observed during these tests, especially the plane frame test, was the failure of these connections. You see, the bolts are missing in this connection, and this happened while the fire was cooling down. Because when the fire was cooling down, initially the beam has expanded from its original position, and when the temperature was reducing, it was trying to come back. And when it was trying to come back, the outside beam was at its location and it was coming back, and that is why kind of tensile force was developed at this connection. The outside member was at room temperature, it was not coming back. Only the inside member which was heated was coming back, and it has kind of pulled it. And because of the pull, the bolts have failed in this connection. And the reason for the failure of these bolts or connect is because of the cooling down, and which people are ignoring the cooling phase of the fire. They are ignoring completely in the standard fire test, and that is why it is so important in the when we are studying the behavior of fire in the structures, behavioral structures exposed to fire. And similar to these kind of milestone events in the context of experiments, some modeling milestone have been also established. And these modeling uh, these models were prepared by calibrating the model of these tests, the restraint beam test. As I have mentioned you, it is considered as the best test to calibrate your finite element model. So they modeled this beam here. As you can see, the shaded region is the restraint beam, and they exposed it to the same kind of fire load as it was exposed during the testing. And they have recorded the temperature mid-span deflection behavior. Here you can see the black graph is representing the temperature mid-span deflection through the experiment, which they have recorded when they were conducting the experiment, and the purple line is through the finite element simulation, the model which they have made on the computer. And the finite element model is also giving them the reasonable accurate behavior, very close to the experimental time deflection curve, temperature deflection. And once they have achieved, they have calibrated their model. Now they can study this beam with different fire scenarios, with different loadings, with reducing the capacity of the steel. So they did conduct that parametric study. Here in this graph, you can see they have increased the amount of load which was coming from the top. From the top, there was some load coming on the beam in the experiment. They have increased it to the double, and they have observed that the change in the deflection is very marginal. It's very low increase in the deflection with the increase in the load with a value of factor of 2. And similarly, they have also conducted this simulation by reducing the strength of steel by half, as you can see here. 50% less steel, 50% more steel. These three graphs. The purple one is exactly same steel as it was in experiments. The green one is 50% more, and this one is 50% less steel as that of experiment. And they are also not affecting the behavior of this beam significantly. They are also giving the similar kind of temperature deflection behavior. So the conclusion, the lesson which were learned from the Cardington test are the local buckling happens in the beam when it is exposed to fire because it is trying to expand, and the compressive force bend the beam at the local location. That is what we call local buckling. And the increase in the load does not affect the temperature deflection behavior of the beam significantly. And so is the case with the increase or decrease in the size of the steel section. That does also not affect the behavior significantly. And the cooling behavior of the fire damages the connection, damages the steel and the concrete, everything. The cooling phase is so important. It is so disastrous for a structure that it cannot be ignored. It has to be considered when studying. If there are any questions from the audience, and I would be happy to answer them. And if due to the time constraint, I am not able to provide all the answers today, then you could always drop your questions through the email, and my email ID you can find on the front slide of this webinar. Thank you so much. Thank you for attending this webinar. I hope I have given you a basic understanding about the behavior of structures in fire. Thank you.
Thank you, Dr. Mustesin, for this very amazing presentation. So if anybody has any question, please, you can ask now. I will wait for 2 minutes if anybody have any question. You can type in the chat box. And as he said that the presentation in first lecture, in first slides, he has his email, Dr. Mustesin email. So within 1 week, as I told, that we will put this lecture on a YouTube channel, our SFPE Hong Kong chapter YouTube channel, you can find there. until at this moment, I have no questions so far. So let me, I will try to ask some question. So as this presentation is providing us the basic understandings of interaction of the structure and fire. Yes.
Yeah.
So how could one can enhance their knowledge in this field and can know more about how the fire and structure are interacting?
Yeah, Atif, that is a good question, because in this presentation I have provided only the basic details about the interaction of structures with fire. But if someone is interested and want to pursue research in this field, then they need to know more than this. And I would suggest that they should try studying the behavior of individual components first, such as the beam and the column, and try to find out the amount of stresses in the form of numbers, that what amount of stresses are coming because of the fire. Then they would have an idea about that, okay, these much of stresses have increased, and for these extra stresses, how much extra material would they need, or how much extra size of the section would they need. Once they have the basic idea about the design of different sections, then they would proceed to apply these concepts to the whole frame or the whole building. And to study the behavior of whole building, I would suggest then start learning some finite element software, because to understand the behavior of a bigger structure, they can't be solved using the analytical model or using the closed form solutions. You need to have the finite element models. So yeah, I would suggest to finally go for the finite element models to understand more in this field.
Thank you, Dr. Mustesin. So still, I do not have any question from the participants so far. So as we still have 9 minutes. So for the information of the participants, I would say this, our chapter, this Hong Kong SFPE student chapter, which is a SFPE. SFPE is one of the biggest organization of the fire, which stands for Society of Fire Protection Engineers. So if any student who is not the member of SFPE, they can go and become a member of SFPE. It is a free for students, and it's a very nice platform to learn more about the fire. And you can have every week or monthly, you have a free webinar from this society. So you can go there. So there's one question. I just have one question. How Mr. Wu Xiqiang is asking that how to know the large deflection at the end of the column is due to the material degradation or by local buckling?
The deflection in a column or in a beam due to local buckling are generally in the initial stage of the fire, because as I have mentioned, when the temperature starts increasing, then there is a compressive force in the column, and this compressive force is mainly the reason for the local buckling. And towards the end of the test, or towards the end of the fire, these high deflections, which we call sometimes the runaway deflections, these are mainly due to the extreme degradation in the material strength. So they are not because of the local buckling, they are because of the real loss in the strength of the material, in the elasticity of the material.
Thank you. Any more participant? Any more questions? Yes, we still have 7 minutes. So another question by Nan. She's asking, I understand cooling phase is very important, but during design, how can we consider the cooling phase design? Like we don't know if the structure member failure during heating or cooling phase.
So to understand the effect of cooling phase, you need to first analyze your structural member, that if the cooling phase is affecting or generating significant stresses in your structural member, then only you can have the idea that cooling phase is important or not. If the cooling phase is not able to generate significant amount of stresses into your structural member, then I hope you don't need to worry about the cooling phase. But if your member is having a good amount of restraint at the support, then I hope the cooling phase would induce a significant amount of stresses in the member, and then at this for this kind of situation you need to seriously consider the effect of cooling phase on the performance of your structural member. I hope I answer your question.
I hope so. I hope Nan get the answer what she was looking for. So I do not get any more questions, but I still have 5 minutes, so I will wait. And regarding, I was telling about this SFPE chapter. If you want to be once you become SFPE member, that I told you for a student, it's a free membership. And if you want to be a member of SFPE Hong Kong chapter, which is it's the first chapter in the Asia student chapter, so you can join us in this group. So you can just email me or anyone from the BSc department to Dr. Xinyan Huang and I or other members. And we have a webinar almost once in a month or sometimes twice. So you can attend this kind of webinar to, you will have one CPD certificate and you will be in touch with the new information about fire. So I guess we have no more question and we can wrap it up. And thank you, Dr. Khan, for this wonderful presentation. And thanks to the participant for joining. And I think we have very good attendance. That's more than 83 still out there. And please, and I want to thank again to the participant and for the people, students or people who want certificate, we will send their certificate within 1 week. We'll try to send, and once we get the data that how many people who stayed on entire session, online and entire session. And thank you very much.
Thank you, Atif.
Thank you again.